Let's examine a few trends in solid surface energy and then look at some ways that surfaces use to mitigate the energy cost of creating surfaces. If we look at this table, we can see at the very bottom we have solid argon. So we know argon's a noble gas. If we get it cold enough, we can solidify it. And we can see this is an extremely low number for the surface energy. And that makes sense because the argon atoms in argon solid are just held together by dispersion forces, so relatively weak. If we look at lithium fluoride, it's quite a bit higher. We know we're held together by ionic forces. If we look at magnesium oxide, it is an ionic compound, but when you have two highly charged ions like magnesium and oxygen, there tends to be a degree of covalent character to the bonds. And so this is really a ceramic. So you've got quite a bit of covalent character and hence stronger bonding and a higher surface energy. If we go to diamond, we know that we have very strong bonds. It's a network solid, so we have to break a lot of covalent bonds to make a diamond surface. And so we have a really high energy cost, a very high surface energy. So when we produce a solid, we can occasionally cleave on a very unfavorable plane. So if we look at the silicon 100 surface, we can see it's highly corrugated. We've got rows of atoms. If you go to this website and punch in silicon and choose this crystal face, the 100 face, and start moving this around, tilt it at a bunch of different angles, what you'll see is that these silicon atoms are sitting on top of atoms directly below them, like this. Which means these atoms on the top are bonded here and here. They're only touching two other atoms, the ones beneath them. They're not touching these on this side row below or this other side row, and they're not touching each other, so these ones aren't touching. So they only have a coordination number of 2. So since the bulk coordination number is 4, it's cost us basically half our bonding energy to make that surface layer. And whenever we produce a high energy surface like this, one way the surface can respond is by reconstruction, where the atoms actually rearrange a bit in that top layer or 2 to accommodate the bonding. And the easy way to do this, each of these silicons you can think of as being sp3. So there's got 4 lobes of bonding. So it's attached here, and it's attached here, and then orthogonal to that we should have 2 orbitals up here, but those aren't bonded to anything. So they're just dangling orbitals with nothing to bond to. Well, the same is true over here. So if this row leans this way and this row leans that way, they can form a bond. And so we're going to form a bond between this atom and that atom, this atom and that atom, and so forth. And then we could do the same thing with this. So we could link this atom to this atom, this atom to this atom, and so forth. That's called a 2x2 reconstruction. Looks something like this. If we look at this, we can see we had a row of atoms that leaned a little bit to the left and a row of atoms that leaned a little bit to the right, and they formed a bond. We have the same thing over here. So we have these neighboring rows that paired up. And that meant that we regained 1 bond for each silicon atom, so the energy cost was just cut in half. Now that wasn't for free, of course. We had to create a little bit of angle strain in the underlying bonds because each of these atoms had to tilt a bit, but still it's worthwhile. And so normally, if there's a really high energy surface that's created when a solid is cleaved, there'll be at least some degree of surface reconstruction.